Hello, thank you for tuning in to Black Death, an SIR model, a presentation by Jake Cromer and Kevin Jones. We will explore a mathematical approach to modeling an epidemic that occurred over 600 years ago and see how this modeling can be applied to contemporary issues. First, some background information on the Black Death. What is the Black Death? The Black Death was a name given to the plague epidemic that devastated most of Europe during the mid-14th century. While statistical data tends to vary as records from 700 years ago aren't always accurate, the estimated death toll was between 25 and 30 million people. And back in 1350, this represented almost 50% of the European population. It took 150 years for the European population to recover to pre-plague numbers. Now, what caused the Black Death? It's the name given to the type of plague caused by the bacterium Yersinia pestis. It was originally transmitted from fleas on rats or from flea bites directly, but human-to-human contact became the predominant form of transmission. Black Death is used interchangeably with bubonic plague. The swelling of the lymph nodes and the accompanying black sores, known as buboes, are where these names come from. The sores were due to internal hemorrhages, and other secondary symptoms included joint pain and high fevers. The disease progression follows the trade routes of the day. It originated in Eurasia, and then it proceeded to spread in a counterclockwise direction through Europe. So what exactly is an SIR model, and how can it be applied to the Black Death? An SIR model is a form of compartmental modeling. It's a method of simplifying a mathematical model in epidemiology. The first compartment, S, is where all members of a population will start. They represent 100% of a population that is susceptible to the disease. In the simplified model, those who are capable of spreading the disease to others are moved to the I category for infectious. Once that individual is no longer capable of spreading the disease, they are moved to the R category. This can either mean they are deceased or have recovered from the disease. Either way, they have been removed from the infectious category and are no longer susceptible to contracting the disease. For a disease with a lower rate of lethality, this can also mean that the individual has produced antibodies. In this model, N represents the total population. It's the sum of the three compartments, S plus I plus R. We're operating under the assumption that the death rate is approximately the same as the birth rate, and as such, the population in the model will remain constant. Here are a few more basic assumptions that we're going to make. The incubation period of the disease is negligible. Once an individual is moved from the S to the I compartment, they are immediately able to infect others. Everyone is equally susceptible to infection, and there's no chance of reinfection after removal. Additionally, R of 0 will be 0. It's logical, considering no one should be removed from the model at the start of it. The model will start when I of 0 is greater than 0, because without an initial infection, there will be no epidemic or spread of the disease. Here are the three basic differential equations we'll be looking at to show the changes to each compartment. Beta represents the contact rate. It'll dictate how quickly people will move from the S to the I categories. The gamma value represents how long a person is infectious for. For instance, if the disease is transmissible for 10 days, the gamma value will be 0.1, as 1 over 0.1 is 10. We can use the ODE45 function in MATLAB to run the three differential equations simultaneously. Here's a brief description of each field. This is where we input our initial conditions for the x vector. The S of 0 is 70, which represents the population of Europe in millions. As previously stated, I of 0 has to be greater than 0, and we assumed that R of 0 is 0. And here is where we define the starting and ending points of t. And finally, this is the function being called. In a separate M file, we've defined the SIR function with the three equations shown below as the x vector. This graph shows the results of the ODE45 function. As you can see from the start, the susceptible values match our initial population while the I and the R values are at 1 and 0 respectively. The peak values shown here show the point at which the maximum infections occurred in the two different cases that were run. On the right side of the plot, the Y value shows in millions the individuals who remained in the susceptible class. That's to say they were not infected. Once we reach the end of the plot, the sum of the S, the I, and the R are still equal to 70. We assume the death rate is approximately the same as the birth rate. This doesn't include deaths from the disease, and as such the N will remain constant in this model. Here's the MATLAB output. The second line is significant because this represents the strain on the healthcare system. During the 14th century, this became the burden of trying to remove bodies, which led to a whole new set of issues in sanitation and the arrival of new disease concerns. In present day, it's more a matter of resource management, such as hospital capacities. From the total infected, you can see that approximately 82% of the total population was infected with the Black Plague. And as we originally speculated, the death toll was between 25 and 30 million. Assuming a 50% mortality rate, the model shows that the deaths are around 28.89 million, which falls within that range. Here, we've isolated the infectious curves from the previous plot. The blue was the first run with a 0.004 contact rate. The red curve shows the results from a 25% decrease in the contact rate to 0.003. The peak has been shifted, but it's not a 1-to-1 ratio with the change in the beta value. The shift to the right means that the rate of infection is more spread out. So we've seen that decreasing the contact rate decreases the maximum number of infections at one time, but what happens if we reduce that contact rate even more? So here in this plot, we reduce the beta value another 25%, so now it's at 50% of the original value. And amazingly, with just a 50% decrease in the contact ratio, there was a 79% reduction in the max infections at one time. While we were originally focused on modeling an epidemic from over 600 years ago, the concept is the same. We can adjust the parameters of the model, whether it's the contact rate, the infectious period, or the population. This has allowed us to see the effect of the mitigation efforts on the graph and, in a sense, flatten the curve. While a more complex model will undoubtedly give a more in-depth look at what happens during an epidemic, even this simple model can give you a basic understanding. Here are a list of references we use to compile information. Thank you for watching.